Today on TestCase TV, we're going to look at wattage with resistors because that's the next thing we need to account for. If you choose quarter watt resistors and you give them more than a quarter watt, they get hot and burn. So let's talk about our scenario. We've ordered some LEDs from Amazon, and the LEDs that came in are from this bag. Now you'll notice the bag is empty because we have populated a couple boards with 50 LEDs. Some of the notable features of these LEDs is the 20 milliamp rating for current and the 3 volt to 3.2 volt forward voltage. So that means that that's the part we separate from our equation when we do Ohm's law. Now with that out of the way, let's look at the board. We're going to start with this, which is our 50 LED grid. What we've done here is taking half of that 100 bag and solder these so that all of these LEDs are in parallel, which means each one of these LEDs has access to both the positive line and the ground, or the negative line, which means every one of these guys has access to both the power and the ground for our DC power supply. What I have done is accounted for the 3 volt voltage drop, and I've set this guy to 8 volts. So it means all of our math is going to be 5 volt as Ohm's law dependent, and then I'm going to choose a resistor that would allow 0.1 amp. And the reason that is because it's 20 milliamps per LED times 50 gives us our 0.1. Now that all makes sense so far, but what we haven't seen is what happens when we take a resistor that is rated for a quarter watt and we're essentially going to give it half a watt. Is that right? Let me think about this. 5 times 0.1, 0.5. Yeah, so half watt. That makes sense. I didn't even need a calculator. That's why I like the 5s. So super simple. I know that the 8 volt source isn't exactly a normal thing to use because you got 9 volt batteries, you have 5 volts, but it makes the math easy for this. So follow along. It's not bad. With that being said, that brought me to a 50 ohm resistor. I don't have 50 ohm, but I have a 51. And as we've talked about before, you get kind of close, right? There's not a need for an exact resistor to get what you're trying to do, and we'll roll with that. I've already attached my 51 quarter watt resistor to my negative side, and the resistor itself could be attached to both negative or positive. It doesn't matter as long as it's in line with the circuit, because that's the current that it's limiting. I'm going to attach power momentarily so that we can see that it does in fact light the lights as we expect. And one, you can see how pretty this thing is that I had Roger here help solder.
Oh God, no.
Let's do this. So ground first. And then I'm going to attach my positive. And we do in fact have lights. Pretty. Now, that was only for a moment, and this little guy is already warm to the touch. So let's see how long it takes for it to be too warm to the touch. So bring this up, and you'll notice, just a side note, that I currently have this wire flexed and it's staying there. That's one of the happy side effects of using solid core wire, is so that I can do this bending and flexing. So a static install solid core can be a nice little add-on. So let's go ahead, see what happens when we give it too much wattage and how long until it smokes. Once again, attaching my ground. Safety glasses on. My red. It might take a little bit. Getting warmer. It's kind of toasty. I can still touch it. And now it's too hot for a touch. So this is one of those things where if we've done our math and we've put everything together, but we didn't account for wattage, when you do stuff like wearables for cosplay, costumes, or whatever, you essentially created a tiny little heater inside your outfit or electronics. And that could be problematic for many reasons. So one of the reasons we're covering this is so that you don't have to get burned And, ow, that is hot. Although I don't know if it's actually going to burn out. Still waiting. This part might take a while.
5 minutes later.
I think I'm going to crank it up. Just because. Like, we can see what fails, but I don't know if that's the right solution. Touch it. Touch it. Touch it for science. That was nothing. There was nothing.
Oh,
It's
hot.
no. Give it a good squeeze. No, give it a squeeze.
Oh no, I felt that. Oh,
No,
I
you
definitely
didn't.
Felt that.
You did not feel that.
I did feel that.
How did no? I call
definitely did feel
shenanigans.
No.
See, nothing. That wasn't touching it. I saw air.
Ooh. I feel it.
The question is, do you smell it? Like, come here and try to smell this.
Can the audience smell it?
Well, they can't, but if they do the same project, they can. Look. Like, does it smell like burning?
Ooh, yeah, that smells like burning.
So it smells like burning. We're not seeing it burn on the camera. I'm not seeing the smoke come out yet. But, I hate being impatient because this part sucks.
I have a lighter.
Oh gosh. Me burning it now cosmetically makes it look like doo-doo. Forget this. I'm cranking it up. I'm impatient. Screw this. There we go. All right. Well, that's a thing. The resistor has cooked. So no matter what I crank it up to, it's not lighting up now. So the question here is, when the resistor fails, did it create an open circuit or a closed circuit? Because if it did closed, we would have just burned out all these LEDs. If it did an open circuit, then only the resistor burned out, this little smoky mess here, into what we need to replace. So I'm going to desolder this after I remove the power. And we still have light. So the only component that just burned out was the resistor itself. If we're going to pull half a watt, then there's a couple options we can do. We can find a resistor that can allow for half a watt or even an entire watt, and then it's not stressing the component, which means we're not going to dissipate so much heat that everything burns out. Or we can get creative with the same resistors that we just used in how we align them. So let me explain. Oh! So what we just did was one resistor, and this one was 51 ohm. And that one we were giving it 0.5 watts, but the resistor itself was only rated for 0.25, right? So when we gave it 0.5, it was hot. It didn't completely burn out. But when we cranked that up to an entire watt, then that's when everything started smoking out, despite us having already played with the lighter just for fun. 0.5 watts and a 0.25 did not make it do critical fail of catching fire. All the smoke came out, and like it was just super hot to touch. So that gives us a talk about like safety factors. But when I went above and beyond to 1 watt, then it immediately started smoking out. It got fuzzy, and then it burned out in such a way that it created a break. So it was no longer allowing any current through. So the internal structure of the resistor was just, it's like, nope, none shall pass, right? So how do we go about dealing with this heat and the wattage issue? One thing that we can do, which is getting creative with our resistors, is connecting several of these resistors in such a way that we still have the same resistance, but we allow for more current to go through, or a higher wattage tolerance. So we're going to talk about resistors in series first. If I have two of the same value resistors, so we say 51 ohm, so we'll do 5, 1, 5, 1. What they're going to do is be additive. So then this whole section will act as one resistor of 1, 0, 2.
That says 105.
I was going to say, my 2 just got backwards. Nope. All right, hold on. I got this. Nope. I draw upside down 2s. Oh, gosh. How's that?
No! Deuce.
Okay, hold on. Boom. Legible. But now it doesn't match the other ones.
No!
All right. So, with 251... Does that math up? Yeah, okay. 251 ohm resistors in series, they're going to act as one 102 ohm resistor. But since all of the current is still going to go through this line, one of the side effects is it's still going to be a 0.25 watt resistor setup because everything's still going through. Plus, considering the circuit that we're dealing with and we accounted for 51 ohms, having 102 means all of the current that we're expecting or needing will no longer be able to get through and the LEDs won't light up. So now let's talk about what happens with resistors when you put them in parallel. So the same 51 ohm resistor that we're going to look at. Now if I put those side by side and say they're the 51, what's actually going to happen is the load is going to be split between the two. So electricity is going to be like, hey, I got 2 pads. Let's go. And what that's going to do is it's going to have, I'm going to get really good at my upside down 2s. It's going to have the resistance of each one because it's splitting the difference. So what that means is, since I have quarter watt and quarter watt, if I'm sending half watt, they'll be able to take that load, but now I have halved my resistance. So what's going to happen is the current that we allow to the LEDs is going to be too high and it's going to burn them out. So that doesn't suit us either. So a series set makes it so that there's not enough current and it's same wattage. Parallel set allows for higher wattage but not enough current. So why not combine the two? So now we're going to combine both series and parallel resistor sets to see if we can't accommodate both the current draw we need and the wattage tolerance. So let's start with a series set. Draw it out and do it again. Okay, so that's series, and we already know that that's going to be 51 times 2. And the reason that is because they're series, so it's additive. Then I'm going to take another set just the same as what I did, and it's going to be parallel this time. All right, and this one will also be 50. Oh, that is not right. This one will also be 51 times 2. When we do the parallel, as we just talked about, what that's going to do is that's going to have each of the sets or the resistors. So if we're treating this like a 102 and this like a 102, what that means is we'll actually be getting rid of the times 2. So now we have a 51 ohm resistor made out of 4 51 ohm resistors. And the reason this is important is because now we can tolerate 0.25 and 0.25. So this will tolerate a 0.5 watt load on the system. So that's one way to get around it. If we're drawing 0.5 and we do a 0.5 watt, even though it'll be safely used, it's still going to generate heat. So take that into consideration when you're actually building out bigger circuits, and try to plan so that your forward voltage drop, like when you put LEDs in series versus parallel, you can actually make the voltage drop go work for you so that you have less heat and less current going through your entire system. So that's part of why we're talking about this. Now that we've got this understood as far as how this will double, but putting in parallel halves it makes it all the same, but this configuration allows for more current, let's go ahead and add that to our previous circuit that we made with the 50 LEDs and test that nothing burns out. It's all good. So I'm going to take this configuration that I have here. So this is exactly what I just drew. It was two sets of LEDs, This is two sets of resistors in series and parallel to allow us the same value, but it'll allow for a higher wattage load, which should make it safer for installs and stuff. And it's one way of accommodating this issue. Granted, you could always get a resistor of a higher wattage tolerance, but when you're out in a project and you don't have access to a store with resistors, this is one way of dealing with that scenario specifically. So let's go ahead and attach it, add some power, and confirm that everything does as we expect. So I got my LEDs here. Now I have already pre-tinned my wire. I'm going to add a little bit of solder to my iron. Like so. So that's there. Attach this again. Now I'm going to add the ground first. And then my positive. So it works just as it did before, only now it's not going to get near as hot. It'll still get a little warm because we're at the max rating that these resistors will tolerate, but now at least it's going to function as I expect for a long period.
So, you watched Metal solder all these different configurations. I hoped it helped. I hope you have a better understanding about how resistors work with your electronics. And as always, if you like what you've been seeing, if you've been finding this helpful, don't forget, we do have a Patreon link that you can find below in the comments section. And also, don't forget, you can put questions, comments, or any concerns about this entire mad ordeal we're going through. So you know what? Happy hacking, guys. We're out.
Seriously, I leave to take one shit and you just take over my show. No explanation. Whatever he said is complete bullshit. What we're really trying to say is, have a good time, comments down below. If you support us, Patreon, happy hacking, and I'm out.
I like that. That was good. That was good.